Hello, we are discussing about GATE 1998 ECE paper, and this is a 5 marks question related to analog circuits. Look at the diagram, which is IC555 timer internal block diagram. Using this one, you are going to implement a monostable multivibrator, and as well as you are going to get an expression for the on time of the output pulse. That is, you are going to get the expression for the pulse width also. In monostable multivibrator, you know that one monostable multivibrator is which will be having one stable state and one quasi-stable state. Stable state is nothing but it's going to be a permanent state, okay, until you are going to apply a trigger pulse. It won't change its state. And quasi-stable state, or it is also called as temporary state. Even though you are not applying a trigger pulse, after some fixed amount of duration, it is after some fixed amount of time, it will go back to its stable state. That's why it is called as temporary state. It doesn't require any trigger pulse. But to get the transition from stable to unstable state, it requires a trigger pulse. Okay. So this is what 555 timer. With the help of 555 timer, we can get the stable monostable multivibrators as well as mid trigger. Here we are interested to get the monostable multivibrator operation. That is, by using this 555 IC timer, you are going to get a monostable multivibrator operation as well as pulse width expression. So if you are assuming that one entire this is in a block, okay. So this is what monostable multivibrator diagram. So this block is nothing but given IC555 timer, we are adding two external components, one is R, the other is C, and it is what trigger pulse. So if you are not applying trigger pulse is going to be at VCC, and if you apply a trigger pulse, the voltage at this point is going to be less than 1/3 VCC. Remember that one. Okay, you are applying a trigger pulse such that the voltage at the trigger is going to be drops below 1/3 VCC. Otherwise, it will be always at VCC. Okay. So first one is under steady state. If you are not applying any trigger pulse at that time, it will be under steady state. For monostable multivibrator, steady state is nothing but V0 is going to be under low level. That is 0. Okay. So V0 is going to be 0 under steady state. Since it is 0, we know that when RS flip-flop is going to be having complementary outputs. So if it is 0, definitely you are going to get a 1. And that 1 is going to be connected, which is nothing but very high voltage. That high voltage makes this Q1 transistor into on condition. So that voltage across this one is going to be VCE saturation. Transistor Q1 goes into saturation and its collector emitter voltage is going to be equal to VCE saturation, and that is 0.2 volts for silicon, 0.1 volts for the germanium. But they are very small compared to VCC, they will be assumed as 0 volts itself. So simply collector and emitter are shorted, that is going to be connected to ground. So voltage at this point is also 0 whenever Q1 is on. So that voltage you are connecting over here, which is nothing but 0 volts. So capacitor is going to be storing 0 volts. Voltage across this capacitor is 0 volts whenever Q1 is on. So VC is going to be 0 volts under steady state. So that 0 volts you are applying for the non-inverting terminal of comparator 1. Okay. And this trigger pulse is applying the inverting terminal of comparator 2. So since you are not applying any trigger, okay, under steady state, so the value present is nothing but VCC. VCC, this is the value present is VCC. And according to voltage division rule, we know that when ideal op-amp, the op-amp doesn't take any input currents. That is, current flowing into inverting and non-inverting terminals are always 0. So if a current is coming from this VCC, it flows in this direction. And it won't go this side, even though there is a node and current flowing through input terminal of inverting or non-inverting is 0 for the op amp. So this current flows in this direction. Same current flows through this R1, same current flows through this R1, same current flows through this R1. Since same current is flowing, all the three R1s are in series. You can apply a voltage division rule. Okay, so VTL, that is threshold voltage connected to lower comparator, that will be equal to 1 by 3 VCC you will get. And VTH, threshold voltage for the higher comparator or upper comparator, this is 2 by 3 VCC. Okay, since all the resistors are same, you are going to get 1 by 3rd, here 2 by 3rd, it is total. So now if you are checking these values, according to this one, we know the comparator operation. Comparator output is going to be, if it is plus and it is minus, this is V0. Okay, voltage at non-inverting, voltage at inverting. V0 is going to be at VCC or logic 1 if voltage at non-inverting terminal dominates over voltage at inverting terminal. Otherwise V0 will be 0 if voltage at inverting dominates over voltage at non-inverting. So check about this one. Voltage at non-inverting terminal is 0, voltage at inverting terminal is 2 by 3 VCC. 2 by 3 VCC is higher, so negative terminal, voltage at non-inverting terminal dominates. Voltage at inverting terminal dominating is nothing but output value is 0. And here non-inverting terminal of comparator 2 is at 1 by 3 VCC and inverting terminal is at VCC. So this is 1 by 3 VCC, this is VCC. VCC dominates. So again the comparator output is 0. So for the RS flip-flop, if you apply R is equal to 0, S is equal to 0, that is next state is same as present state. Okay. So under steady state V0 is equal to low, and that makes R is equal to 0, S is equal to 0. For RS flip-flop, next state is same as present state. Present state is V0 is equal to low, that is Q is equal to 0. So it continues the same state as Q is equal to 0, that is nothing but V0 is equal to 0. So if you are not applying any trigger pulse, Q is going to be 0, Q bar will be 1, and that 1 will make Q1 on condition. That on condition makes capacitor voltage to 0. So that again R will be 0, S will be 0, you will get. This cycle repeats and it will be in the same state as low level. That's why only it is called as stable state. Once it enters into low level, at that time it won't change until a trigger pulse is going to be applied. Okay. So let us assume a trigger pulse is going to be applied for this one. How it is going to be changes, how the output changes, and how it comes back to its own stable state after some predefined amount of time, and how to calculate that predefined amount of time, that is pulse width duration. Okay. This is what the diagram we are looking at. Monostable multivibrator using IC555. Now we are applying a trigger pulse. Okay. So assume that one at t is equal to 0. At t is equal to 0. Trigger pulse is applied. Trigger is applied. Trigger is going to be a negative going pulse which is having very short duration. Okay, so this we can say it as 0 plus. At t is equal to 0 plus. Okay, so first case, at t is equal to 0 plus, voltage at non-inverting terminal of comparator 2 is at less than 1 by 3 VCC. That is, the value is less than 1 by 3 VCC, and we know VTL is 1 by 3 VCC and VTH is 2 by 3 VCC. Okay, and now the value across this inverting terminal of comparator 2 is going to be less than 1 by 3 VCC, so that non-inverting terminal of comparator 2 dominates, that makes the value of output of comparator 2 to go logic 1. That logic 1 you are applying for the S input of RS flip-flop, and at that time what will be the value of comparator output 1 also will check. Since previously output is at low level, so capacitor voltage is at 0 and this is 0 and it is at 2/3 VCC. So 2/3 VCC dominates. So this output is going to be 0. You are applying at T is equal to 0 plus, okay, non-inverting terminal of comparator 2 whose value is, okay, less than 1/3 VCC. Okay, so that makes S is equal to 1 and R is equal to 0, which is nothing but set state. Set state is nothing but Q is equal to 1, that is V0 will go high. Okay, now V0 will go high and Q is equal to 1, that makes Q bar is equal to 0. Q bar is equal to 0, so transistor Q1 switch off, that is nothing but it comes into cutoff condition. Transistor Q1 is cut off, so that now capacitor is not going to be connected towards this node. Okay, so there is a chance that now capacitor can able to charge as the current is coming in this direction. Previously also current will come in this direction, but since it is going to be connected to ground, as the Q1 transistor is on, current flows in this direction towards ground. The current doesn't flow towards this capacitor. Okay, now as this connection is going to be not present, since Q1 is cut off is nothing but open circuit, so no current flows. So definitely now the current coming from the VCC will go through this capacitor. Now capacitor starts charging. Capacitor starts charging. Capacitor charges always exponentially. Capacitor charges exponentially with time constant, with charging time constant, that is product of R and C in the current path. So the charging path R into C, this is a value of R and it is a value of C. R into C is the time constant. Charging time constant is RC. So capacitor now starts charging. Now second case, okay, for T greater than 0 plus, for T greater than 0 plus is, that is a trigger is applied for a very short duration. So again the value across this point trigger will come back to VCC. Okay, now whatever we are going with is 1/3 VCC. Now it will be changes to VCC. So we'll see what happens. Trigger is nothing but very short duration pulse which will be applied for only short amount of time, and for T greater than 0 plus we assume that one trigger comes back to its normal state, that is VCC. So the value present at this point is now VCC, and across this VIL it is 1/3 VCC, and across VTH it is 2/3 VCC. Okay, and Q is going to be having a value of 1 since V0 is going to be high at T is equal to 0 plus, and it is 0 and that 0 you are applying, so that will be in off condition. Since it is off, capacitor starts charging by going through current in this direction. So voltage across capacitor is now increasing, that is voltage at non-inverting terminal is rising, but voltage at inverting terminal of comparator 1 is fixed at 2/3 VCC. Okay, so we assume that one capacitor voltage is going to be less than 2/3 VCC only. Okay, it is greater than 0 but it is less than 2/3 VCC. Capacitor voltage has not reached the 2/3 VCC. Okay, and now if you are going to check what is the value of R and S, Since the value across this point is less than 2 by 3 VCC, inverting terminal dominates, so that output of comparator 1 is 0. And inverting terminal of comparator 2 is at VCC and non-inverting terminal is at 1 by 3 VCC. So that again this will be 0 as inverting terminal dominates. So which makes S is equal to 0, R is equal to 0. That is again present next state is nothing but same as present state for the RS flip-flop. Present state is nothing but with Q is equal to 1, that is V0 is equal to high. Okay, so this state of Q is equal to 1 continues. Since Q is equal to 1 is continuous as previous, that makes Q bar is equal to 0. So again transistor Q1 will be in cutoff condition only, so that capacitor charges. Okay, capacitor charges with charging time constant of R into C. Capacitor continues to charge. Okay, so now we are going for the third case. After some amount of time, from 0 onwards we are starting. So after some amount of time, let a t is equal to Tp, pulse width duration. Okay, let t is equal to capital T or simply capital T you can go with. Okay, Tp or pulse width, a t is equal to Tp. We assume that one capacitor voltage has reached 2 by 3 VCC. Has reached 2 by 3 VCC and it tries to go above that one. Okay, so at T is equal to Tp plus. What happens? Okay, at T is equal to Tp plus, voltage across this one is going to be greater than 2 by 3 VCC. Greater than 2 by 3 VCC. So this non-inverting terminal of comparator 1 dominates, that changes 0 to 1. And since trigger is not applied, so that it will be at VCC only, and this point is 1 by 3 VCC, it is same as this will be in the 0 condition only. This makes, okay, R is equal to 1 and S is equal to 0. R is equal to 1, S is equal to 0, that is nothing but reset state. Reset state means Q will become 0. Since Q will become 0, V0 will go low. Okay, and whenever V0 will go low, that is Q is equal to 0, Q bar will become 1. Q bar will become 1 is nothing but that makes Q1 transistor. Okay, this 1 will go to 0 and this 0 will go to 1, and that 1 is making off to on condition. Q1 comes into on condition. Since Q1 comes into on condition, whose VCE saturation is going to be? VCE saturation is approximated as 0 volts. So collector and emitter are shorted. Collector and emitter are shorted. Okay, and this collector is going to be connected to capacitor. So capacitor discharges instantaneously. Capacitor discharges. Capacitor discharges instantaneously. Since capacitor is now connected to ground, it discharges instantaneously. So again the voltage across capacitor is now 0. Okay. So this is what we are going to study at T is equal to Tp. Remember it. At T is equal to Tp. Now at T is equal to Tp plus, what happens? We will see. At T is equal to Tp plus. At T is equal to Tp, capacitor has reached 2 by 3 VCC, and at T is equal to Tp plus. Okay, capacitor voltage is at 0 volts. Okay, and previously the value is now going with at t is equal to Tp, V0 goes low, Q is equal to 0 and Q bar is equal to 1. That 1 is going to be over here, that makes Q1 transistor on, so that voltage across this one is becoming 0 volts. Okay, now this is 0, again it is going to be at 2 by 3 VCC, this is at 1 by 3 VCC and it is at VCC. So that comparator output is going to be 0 as inverting terminal dominates over non-inverting. For comparator 1 also, inverting terminal dominates over non-inverting. So this is 0. 0 is giving to R, 0 is giving to S. That makes S is equal to 0, R is equal to 0. That is, next state is same as present state. Present state is nothing but Q is equal to 0. So V0 is equal to low only. So V0 continues to be in low condition. Okay, that makes Q bar is going to be 1, which makes transistor Q1 into on condition. So that capacitor voltage always is going to be at 0 volts. So this will be, it doesn't change. Output will be always under low condition and it is called as steady state. Okay, if you observe, this is going to be the graph. Whenever t is equal to 0, you are applying a trigger pulse. As you are applying trigger pulse, this is 0 minus and this point is at 0 plus. Okay, this point is at 0 plus. And from 0 plus onwards, capacitor gets charging exponentially with time constant of R and C, and capacitor can able to charge towards VCC, but because of the conditions prevailing in the circuit, as it is connected across input terminal of op amp, okay, it is going with only VTH. VTH value is 2 by 3 VCC. Okay, and again at t is equal to Tp. Okay, this is Tp plus and it is T plus. This is T minus and it is T plus. Again at T minus this value, this is at T minus and it is at T plus. We are calling it as Tp instead of T. Okay, so this is the duration of pulse. So at Tp minus output will be high, at Tp plus output goes to low level. So this duration is Tp minus 0 is Tp. We are going to calculate this duration. Okay, to calculate pulse width, derivation for, okay, pulse width. For that one, capacitor voltage at any instant of time, okay, at any instant of time capacitor voltage is Vc of t, that can be calculated using this equation. Vc of t is equal to Vc final minus Vc initial minus Vc, if you are writing minus over here, okay, at that time Vc final should always be in opposite sign, but if you are writing it as minus into minus, it will become plus, same sign, so make it as plus. Otherwise, if you are writing minus over here, write Vc final first, later Vc initial into e power minus t by tau. Tau is nothing but time constant. Remember this one. This equation can be written as like this: Vc final minus Vc final minus Vc initial into e power minus t by tau. Like this also you can write, or like this also you can write, minus or plus. This is general expression. This is used to calculate capacitor voltage at any given time. Okay, so now where Vc final is nothing but what can be the final value if capacitor is allowed to charge. If capacitor is allowed to charge, at that time it can reach the maximum value as Vcc. So this will be Vcc, and Vc initial is equal to initial value at which capacitor starts charging, that is 0. Okay, and tau value, that is time constant So product of resistance and capacitance, product of effective resistance and effective capacitance in the charging part, that is R into C. So Vc of t, now I can write like this: Vc of t, Vc final is Vcc plus Vc initial is 0 and it is Vcc into e power minus t by Rc, and this can be written as Vc of t is equal to Vcc, if you take common, 1 minus e power minus t by Rc, and we know that one at t is equal to t, that is at the end of pulse width, at the end of pulse width, capacitor voltage is going to be charging 2 by 3 Vcc. So substitute these values in this general expression. So 2 by 3 Vcc is equal to Vcc times of 1 minus e power minus Tp by Rc. That small t is now replacing with a specific value, that is Tp, and at t is equal to Tp, capacitor voltage is 2 by 3 Vcc. So Vcc get cancels. 2 by 3 Vcc is 1 minus Tp by Rc. So if you are writing it, e power minus Tp by Rc is equal to 1 minus 2 by 3, that is 1 by 3, and if you are taking reciprocal of both the things, at that time it will become e power Tp by Rc is equal to 3. So from this one, Tp is equal to Rc natural logarithm of 3. Rc natural logarithm of 3 is around 1.1 Rc. So the duration of pulse width for the monostable multivibrator is 1.1 times of Rc. By changing the R value, Rc value, you can get the desired pulse width. So this is derivation for the pulse width, and previously what we have discussed is operation of monostable multivibrator using IC 555. Thank you.